Namaskar, good afternoon, good morning, good evening, depending upon which part of world you are. आप सभी का PRL के अमृत व्याख्यान में स्वागत है, अभिनंदन है. A very hearty welcome from me, Anil Bharadwaj, for PRL का अमृत व्याख्यान. This is the 13th व्याख्यान of the 75 episodes of series of Vyakhyans, which is being organized as a part of PRL 75 years of legacy of history in fundamental physics and space sciences. Established in the year 1947 by father of Indian space program, Dr. Vikram Sarabhai, the PRL's Platinum Jubilee, that is PRL at 75, coincides with 75 years of India's independence. Hence, it's a joint celebration of development of science and technology in India by PRL under the banner of PRL ka Amrit Vyakhyaan. Today, we have a distinguished speaker, that is a Vyakhyaan Karta with us, Professor Jonathan Tennyson from University College London. And he will be speaking to us on what are exoplanets made of, molecular lines list to aid the characterization of exoplanets. Exoplanets, as we all know, is a very interesting topic nowadays. And with increasing number of exoplanets being discovered, this is a very hot topic, not only for PRL or for any astronomer, but also it is very enriching for us to know whether the life exists outside our solar system. And exoplanets is the place to look for life. So with this, I would request now my colleague, Dr. Bala, to introduce Professor Jonathan.
Thank you. Thank you, Professor Bharadwaj. It is a pleasure and honor to introduce Professor Jonathan Tennyson, Fellow of the Royal Society. Professor Jonathan Tennyson is a physicist whose research covers a range of topics on the theory of small molecules. He is a massive professor of physics and head of the Department of Physics and Astronomy at the University College London. When you talk about electrons colliding with molecules and their spectra, we have to mention Professor Jonathan's work. His work on electron collision with molecules has implications to atmospheric processes, astrophysics, neutrino mass determination, and radiation damage in biological systems. He leads a large and successful research team at the UCL who study the way molecules absorb and emit light with a particular emphasis on astrophysics and the Earth's atmosphere. Of course, so today's talk, it is the Earth's atmosphere, but not in our solar system, and like how to study the Earths that are in the other solar system or the giant Earth-sized planets. With this short introduction, I'm happy to put it to Professor Jonathan Tennyson. We'd like to hear from you. Thank you.
Okay, thank you for the introduction. I will share my screen. Okay, just go to full screen. It did this earlier correctly. There we are. Okay, so I hope you can all see that correctly. It's a great pleasure for me to talk to you. I have been once to PRL about 14 years ago and given a talk, and I enjoyed my trip very much. So it's nice to be back virtually, though, to be honest, it's more fun to be there. So I'm going to talk about our work calculating molecular line lists. And just to add one slight correction to the introduction, I was head of department here, but actually I stood down when the ERC very kindly started funding this project. So I was able to go back to spending my time doing much more of my time doing pure science rather than doing administration. So I'm from University College London, which is, this is a picture of the front courtyard at UCL, looking very splendid, though actually, to be honest, where the picture is taken from at the moment has a pop-up lecture theatre sitting in it. And UCL is quite an interesting university because it was founded in 1826, at which point England only had 2 universities, and you can guess that they were Oxford and Cambridge. And to go to university, you had to be what was called a communicating member of the Church of England. So universities was closed to members of other Christian faiths or any other faith or people of no faith at all. And a group of free thinkers decided it was a nice idea to found a university in London, which was open to anyone, independent of race, religion, creed, or whatever. And indeed, that was originally founded as London University in 1826 and became University College London about 10 years later when they formed the Federal University of London. And it's had a very interesting history since then, including the fact that Gandhi studied at UCL when he did his law degrees. Now, he disliked London intensely. History does not relate what he thought of UCL in particular, but that's another subject altogether. So we have still, if you come visit us here, preserved for all to see the remains of Jeremy Bentham, who was not the founder of the university, but who was very much the inspiration for the founder of the university. He was a very interesting utilitarian philosopher, jurist, and social reformer. So if you come and visit me, I will personally introduce you to Jeremy Bentham, who lives just down the corridor from me. So I'm going to talk about what exoplanets are made of, and experience has told me that if you put a question mark in a title, it normally means you're not going to find out the answer, and I'm afraid you're not going to find out the answer today for that, because we don't really know. We're on the edge of knowing, and I'll talk a little bit about future developments, which I think are going to make a big impact in this topic. So I'll talk a little bit about the current status. I'll talk about the ExoMol project, the original one, which I stepped down to head a department to run, and where we've got to. As a sort of light relief, I'll talk a little bit about our discovery of water on K218b, which is a potentially habitable exoplanet. It's at least one where water is expected to exist in the right phases to be habitable. And then I'll talk about the latest project I just started a year ago called the ExoMol HD project, also funded by the European Research Council. So this is a relatively old picture, but it hasn't really changed very much. We now have discovered somewhere approaching 5,000 exoplanets, slightly under in the last 20 to 25 years. But if you plot them like this, and this is a plot of the orbits of the planets measured.
Jonathan?
Yep.
Can you just click on the hide below? There is this white
bar. Oh yeah,
bar
okay, yeah. I didn't know whether you could see that as well. Certainly it's annoying for me.
Okay.
Is that better? Okay, yep.
That's
So this is a plot showing the orbital radius of the planets observed in astronomical units, where the Earth's orbit is 1 astronomical unit against Jupiter masses. And what you can see is that there's a strong bias here to planets which are much bigger than the Earth and which orbit much closer their planet than the Earth. Now, there are a few Earth-sized planets which orbit much nearer their star, but if anyone tells you that they've observed an Earth-like planet so far, they're not really telling the truth. We've seen Earth planets in the habitable zone orbiting much cooler stars than the sun, where the zone is much nearer. And I'll talk about that in a bit. But at the moment, a lot of the planets we've seen are orbiting very... Can you see my pointer, by the way?
Yes.
Yes, okay. So you can see a lot of planets in this region where they're orbiting their stars very close in, so they're very hot. And that was actually one of the major motivations for us starting this particular project. So if you look at the range of planets that have been seen, there's a strong bias. The original ones discovered very often were hot Jupiters, gas giants orbiting very close to their star. We're now seeing similar gas giants directly imaged, and we're also seeing a large number of these sort of super Earth planets, which are a bit bigger than Earth, and some of them are indeed very hot, as I'll show you on this picture. So we look at the temperature range. Obviously, we are down here at a few hundred Kelvin, but many of the planets we observe are very much hotter. These super Jupiter planets are often at 1,000+ Kelvin, and indeed, sorry, went the wrong way. There's a planet Kelt 9b, which was discovered 2 or 3 years ago, which is a real poster child for this, and is estimated to be at a temperature of about 4,000 Kelvin. 4,000 Kelvin is actually hotter than most of the stars in our own galaxy. So we have a huge range of planets, many of which are very, very hot. And the original detection method involved looking at the Doppler shift of the planet. So you saw the star oscillating, and the atomic lines in particular in the stellar spectrum would oscillate slightly as the unseen planet rotated around it. And this is a very nice technique, and it's very sensitive to heavy planets such as Jupiter. So Jupiter makes the sun wobble by about 15 meters per second, but the present sensitivity is about 0.5 meter per second. Earth only makes the sun wobble by about 9 centimeters per second. So if you're doing the sort of experiment we can do and looking at our solar system, you'd certainly see Jupiter, you'd probably see Saturn, you wouldn't know that Earth existed using this technique. And this was the technique that won Mayer and Queloz the Nobel Prize 2 years ago for the original detection of a planet going around the star 51 Pegasus, and that planet is called 51 Peg B because the convention is that the star is A and the nearest planet to the star is B and C and so forth. And this is the original detection picture showing a nice sine wave with a period of 4.2 days, which is of course convenient length of time for doing your observation. Another barrier to finding Earth remotely is we only orbit our planet once a year. So to see several complete orbits, you have to observe for a very long time, which is also a barrier to such detections. Now, this is a picture of Venus transiting in front of the sun. This has happened twice in our lifetimes. The first time was very nicely visible from the UK in June 2004, and indeed I got a nice view of it, and I also went on television to talk about it. The second planet actually was on the Queen's Diamond Jubilee Day, and the weather was terrible in London. I got up very early in the morning because that was when you were meant to be able to see it on the morning of the 6th of June, and it was completely cloudy, and I went back to bed again. If you didn't see either of these events, and I'm afraid I don't know what they were like viewed from India, I'm afraid you're going to have to live a very long time to have another opportunity because it's nearly another 100 years before Venus transits again. However, an experiment I wasn't doing, but people were, was actually monitoring the amount of light blocked by the sun as Venus passed in front of it. If you look at that, it's about a quarter of the area of the sun. So you see a reduction of maybe 0.3% in the total sunlight transmitted by the sun as Venus transits. And that gives you the indication that you have a transiting planet. And you can apply the same technique to exoplanets, and you can look for dimming of the starlight as a signature that you have a planet coming in front. And that technique has been used now. It's actually the main method used to detect exoplanets, even though only about 1.5% of all exoplanets actually transit, and that's a geometric effect, just a question of how we view the geometry, we view the star we're looking at from the solar system. But if you can measure both the oscillation of the star, like in this upper picture here, and the transit curve, like in this lower picture here, you can get the period, you can get the mass, you get those two from the upper observation, and you get the radius, or judging by the amount of starlight that gets blocked out from the lower observation, and between the two of them you can get the density. And that gives you some idea of whether you're looking at a rocky exoplanet or a gas giant or something in between. But you can't get more than that without actually going a step further and looking at spectroscopy. So to look at spectroscopy, you need to, of course, look at the different wavelengths of the light. And this was a very early attempt to look at spectroscopy on a gas giant using the Spitzer telescope at 3 different wavelengths, 4 microns, 6 microns, 8 microns. And you can see that you're getting a variation in the absorption by the star, or the amount of light blocked by the planet, should I say, from the star as it transits in front. And you can use this to begin to get some very early detections of what the composition of the planet may be. And in this case, my now colleague Giovanna Tinetti modeled this using a water line list and showed that actually this behavior here was caused by water. Now, actually, the situation was a bit more interesting than this. Giovanna was not at UCL at this point, and she came to UCL and gave a seminar and said, I tried to model this and I think it's water, that the model doesn't work. So I went to her after the seminar and said, what water line list are you using? And she told me, and I said, that's not very good. You should use R1 BT2. And a week later, I got an extremely excited email from her saying, yes, this works. Our line list fits, and you can see the fit here, and it works very nicely. So we sent this off to Nature with tentative detection of water in a transiting exoplanet, and Nature, in their wisdom, struck the word tentative off the title and published our paper. And I started a collaboration with Giovanna, which is still going on. About 6 months later, I hired her as a member of faculty. The great advantage of being head of department, you can do that sort of thing. And as I say, the rest is history. You'll hear more about that as we go on through the talk. So this was a further observation made now using both the Hubble Space Telescope and Spitzer, and what you can see here is in this middle bit, you're beginning to get things which really do look like spectra. So our observation was confirmed. This is actually a different planet, but you can see water, methane, and hazes. The hazes are the blocking of the light up in this region here. So that was very early transit spectroscopy, and that got me interested in the idea that actually we should provide these data for Giovanna and her colleagues to actually make these sort of detections. And that was really the seed of the idea of actually running this project, the ExoMol project, to provide all the data that's needed for making these observations. And the underlying logic of this is that these cool atmospheres, cool in an astronomical sense, so anything from a few hundred to a few thousand degrees Kelvin, are dominated by molecular absorptions. And this is just a montage from Marley and Leggett showing this. So the top line is an M-dwarf star showing very strong absorption by TiO of water. The second is brown dwarfs, and I'll show you another example of a brown dwarf later, showing strong absorption by methane. And here we have another brown dwarf here with even stronger methane. And then this is Jupiter, again with ammonia and methane absorptions. And you simply cannot model these atmospheres without a very large quantity of this molecular data. And again, I'll demonstrate that as we go through the talk. So this is the molecular opacity problem. And the question we had to answer was, how does this affect the atmospheres of exoplanets? So I had done a project already. We used this line list for making the original detection of water in HD in the hot Jupiter planet I mentioned. And this was the BT2 line list computed by a PhD student of mine, Bob Barber, taking 50,000 processor hours, a terabyte of wave functions. A terabyte is not that big nowadays, but 15 years ago, when Bob said we wanted to store the wave functions, actually we had to buy 4 separate computers, and these were known as Bob's towers in the group to store all these wave functions. That required us to calculate 250,000 energy levels for water, and gave us a line list of about 500 million transitions. And that should be compared with about 100,000 at that point, which are experimentally known. And we were able to manipulate partition functions to show that up to a temperature of about 3000 Kelvin, this was 99.99% complete, but actually very rapidly as you went above 3000 Kelvin, became much less complete. And the BT2 line list has been used for a number of applications. The original detection in exoplanet I already mentioned, detection of water in brown dwarfs and M dwarfs, analysis of the atmosphere of Venus. We got very involved in a comet observation. Now, comets are called cold, so they don't need a hot line list, you'd think, but actually they're non-LTE, they're non-thermodynamic equilibrium. We got involved in assigning fluorescence spectra caused by initial excitation by the sun, which used our Einstein air coefficients. A particular interest for this talk was we had a project with 2 of your co-workers, Doctors Ashok and Banerjee, working on nova-like spectra from the exploding star V838 MON, and they had very interesting observations taken over a long time period. We were able to use our line list to show how the water cooled over that time period, having been originally ejected from the star in the original explosion. Of course, water is a very important terrestrial molecule, and hot water gets used for a whole lot of things on Earth. And these are just some of the examples of things that the BT2 line list was also used to look at. So detection of flames in forest fires, high temperature gas sensors, looking at profiles in flames, explosions, water concentrations and explosions, rocket exhausts, and so forth. I'm not going to talk about those today, but a lot of our line lists actually have terrestrial applications as well, but the choice of them is driven by what is good for exoplanets. So in 2011, exactly 10 years ago, I started the ExoMol project. And the idea of the ExoMol project was to provide data for all molecular transitions important for exoplanet atmospheres. And I didn't say this, but I don't measure these things. I do quantum mechanics. That's my core competence. So the methodology was first principles quantum mechanics, and we use experimental data where available. And I recruited a very bright young scientist, Sergei Yurchenko, to come and work with me. He was in Germany. I persuaded our dean that at the end of 5 years funding I had for him, they would give him a permanent job. And to my relief, the dean said yes, and he's now a full professor in the department and my co-worker, and we still work closely together. So The first question you may wonder is why we're doing this theoretically and not measuring experiments. You can get much more accurate data measuring experimentally. And the answer is simply the temperature. So experimental data are very good at informing spectra for studies of the Earth. There's a very well constructed and well-used database called Hydride, which people use for doing all the Earth models. Most climate change models, for instance, use data taken from spectroscopy in Hydride, and we contribute very extensively to Hydride. But Hydride is good, not even as far as the line drawn on this picture, maybe up to 400 Kelvin at a push. It's certainly hopeless at these high temperature. There's Hydrade's hotter brother called High Temp. At the moment, High Temp has very few molecules in, and indeed, it's our data that's largely informing High Temp anyway. So the water in High Temp was BT2, the line list I just talked about. A new version of High Temp is coming out now, but again, with a lot of our data in. So if you're doing lab spectra, you can do them in this region. You can maybe take a spectrum in a flame, but it's a non-LTE environment. And I have analyzed water spectra in flames, in oxyacetylene flames, for instance, but you don't get line intensities. So if you want line intensities up in this sort of region, you really have to do calculations. And these are useful for brown dwarfs, dwarf stars, sunspots, and diatomics actually exist even in the sun themselves, the main sun solar corona, well, not solar corona, the solar atmosphere itself. So that actually, if you're going to go up to these high temperatures, you really need to do the calculations because you can't measure the individual lines with the accuracy you need. And we can do this accurately. And it's interesting, I put a montage of CH4. CH4 is actually one of our less accurate line lists, and we're in the process of improving it at the moment. I'll tell you at the end how. But this just gives you an idea, looking with the best experimental data, that really to
Jonathan?
lines, so 1/40,000th of the number of lines we computed. Hydride now has all lines in it, but that's because they've been taking lines from our computations and putting them in their line lists to ensure that they are more complete. So that was the underlying idea. This is a schematic of our methodology. And obviously a molecule has two forms of motions in it. It has the motions by the electrons and the motions by the nuclei. We need to treat both of those. Within the Born-Oppenheim approximation, you can do that separately. We normally make small corrections due to making that approximation, but I'm not going to talk about them here because it gets a bit too technical. So we start off by solving for the electronic structure of the molecule using standard ab initio methods. We normally use the code called MolPro, and that gives us a potential energy surface and a dipole moment surface. We need to solve a whole grid of different geometries to get that, to get our instantaneous dipole at each geometry and our potential energy at each geometry. We could use that potential energy surface to do nuclear motion calculations, and we use variational methods to do that. That gives you energy levels and it gives you wave functions. The wave functions can be combined with the dipole to give you intensities. We actually store Einstein air coefficients because that's a useful common currency. And the energy levels can be compared directly with the experiment. And normally when we do a straight ab initio study like this, comparison is not very good. So we end up having to refine our potential energy surface using the experimental data. We may need to go several times around this circle until we get something which we're happy with. And then we compute our final line list, which becomes the ExoMol line list. And we have a particular format we store that in. So that's our methodology, and I'll give you a few illustrations. One of the very first projects we did was to do a series of studies on magnesium hydride and calcium hydride. This was actually done by a set of undergraduate students. So Ben Yadin, who worked on magnesium hydride, at that point was an undergraduate student from Oxford who came and did a summer project with us. He then actually came to UCL to do a PhD in a different group than me, and he's now a postdoctoral researcher. But what we did was take a MolPro potential energy curve actually that had been calculated previous by this group Shatesh et al. And you can see the vibrational levels in this. We have a dipole moment curve which looked like this for the molecule. It's ionic here, so you get this straight line curve here, and then it crosses and ceases to become ionic. We solved for the nuclear motion of the curve. We had to refine the curve to get better agreement with the experiment. And we used Bob Leroy's level program for solving for this diatomic molecule. And we get this line list with a not that many lines, 7,000 lines on. And there was a previous one by Yugamop, University of Georgia, looks the same at this level. It's not the same at all. The refinement shifted many of the lines by about 12 wave numbers. That's a huge shift. R1 is spectroscopically accurate. The ExoMol one was not. Slightly more complicated example where we looked at electronic structure, electronic excitation, so row vibronic spectra, calcium oxide. So instead of just doing the ground state here, we did 3 excited states given here. And again, we started off with the previously calculated electronics calculations by Khalili et al. And very large dipole moments here. The transitions here are hugely intense. And we had to refine the curves. We had to, in this case, because we have open shell electronic states here, we had to put in spin orbit coupling. Turns out to be large, 50 to 100 wave numbers in many cases. And to do that, we had to write a new nuclear motion program because LEVEL couldn't cope with those electronic spin orbit couplings and other not relativistic effects in open shell molecules. So I'll mention DUO briefly in a couple of minutes. And then we ended up with a line list here, much bigger. Calcium oxide is heavier, so it has many more lines. We had all the electronic transitions, so 22 million lines, and a spectrum like this. And whereas, I don't know whether you could read this, that's 10 to minus 14 or 10 to minus 13 this peaks at. That may seem like a very small number, but that's Hydride units, which is really per mole instead of per molecule. To get a per molecule number, you have to multiply by Avogadro's number, which is 10 to the 23. So these are actually very large numbers. These are very strong transitions. And whereas this still hasn't been seen astronomically, this line list was used to observe calcium oxide in meteorites in the Earth's atmosphere about 3 years ago by this Russian group. So the line lists can have a variety of uses, not all of which are anticipated when we make this. This is our new diatomic code DUO, which actually has a rather simple form for looking for the Hamiltonian. It considers the sum of the various angular momenta, so the orbital angular momentum, the spin angular momentum, the rotational angular momentum, to give you a total angular momentum J, and then we solve for the problem using a fully coupled basis set, so a vibrational basis set, a rotational basis set, a spin basis set, and an electronic basis set. And we can solve this problem fully in so-called Hunt's case A basis to give our complete solution to the problem. And in fact, I have a student who's just finished putting in hyperfine effects in this. So we have another angular momentum caused by the nuclear hyperfine effects. And that's necessary actually for looking at vanadium oxide, which is a molecule I may mention in a few minutes. So moving on to yet a more difficult problem, a molecule which is really important. I already mentioned it, M-dwarfs. It's really important in exoplanets where it's thought to cause the greenhouse effect. In a lot of exoplanets is titanium oxide. It's thought to stop radiation escaping from the planet caused by rebound from the atmosphere, and in some cases sort of blocks incoming radiation. It has very strong absorptions at 1 micron or 10,000 wave numbers due to these very rather complicated electronic transitions. So you have a whole lot of curves here that we need to consider. It's probably easier to consider the various electronic bands that are observed in the molecule. These are the ones that have all been measured in the laboratory and we were able to use to refine our line list. And you can see they're really quite complicated, quite a few of them. And we were able to produce this so-called TOTO line list. And this is the first hint of actually the extreme temperature dependence here. So if you look at 1,000 Kelvin, you can see that you get big dynamic range in the absorption features. And as you heat up, you get these absorption features flattening out so that by the time you're at 5,000 Kelvin, actually these are very much flatter by several orders of magnitude. And that is typical of what happens in the spectrum. And this is the visible spectrum of TIO. It's well observed. It's easier to observe from the ground because it has strong visible spectra in these various objects. And this has been used for a whole variety of detections in exoplanets I haven't listed here. However, there are other molecules which are even more complicated. Iron oxide, as I'm sure many of you be aware, iron is the fate of a lot of the mass in the universe because it's the most stable nucleus. So a lot of things get turned into iron. So molecules of iron like iron oxide and iron hydride are really important, but they're incredibly complicated. I've counted there are 54 curves we need to consider to get a decent spectrum of iron oxide. We'd have to do all the spin orbit couplings and so forth between them. So whereas we'd very much like to do this, I'm afraid the current situation is summed up by this picture here. It's an aspiration at the moment. There's still more work to do. Now, when I started the ExoMol project, I thought it was going to be the polyatomic molecules, not the diatomics, that were going to cause us the grief. This has turned out really not to be quite so. We've done a number of polyatomic molecules, and where they're computationally very expensive, we seem to have got good solutions to all of them. I'll give you a couple of examples, the first being phosphine, and we had a potential energy surface calculated by Sergei Yurchenko before the project started, using very good quality ab initio theory, and a similarly dipole surface calculated as similar level of theory, but actually in a different project. And we refined these using lab spectra. We solved for the nuclear motion, for which we used the program Sergei developed called Trove, and we had to adapt Trove to get the correct symmetry of phosphine in, and we neglected the tunneling motion. Those of you who know anything about it, ammonia tunnels very strongly. Phosphine, the tunneling has not been observed yet, so we neglected that. And when we compared with Hytram, what we found was that Hytram was missing vast quantities of phosphine spectra. So we did that, and it was a PhD project of my then student, Clara Souza Silva, and she calculated 1.6 billion transitions for temperatures up to 1500 Kelvin. So you can see that when we're getting to these bigger molecules, we're getting order of magnitude difference, many orders of magnitude difference in the number of transitions we need to. This is not our biggest line list. Our biggest line list is 10 times bigger than this. So the line list can get really, really huge. And then we had a side project was, can one detect the tunneling splitting? And we made a prediction where it should be. And the answer is, so far it has a question mark there, so you should have the key. The answer is, so far no one has detected it, though one Japanese group did try using our data to do so. From an exoplanet point of view, the interesting thing about phosphine is that firstly, it hasn't been detected yet. It's well known on Jupiter and Saturn, but hasn't been detected in an exoplanet. It has a nice strong feature here, which should be observable once we get space missions able to observe in the mid-infrared. The two missions I talked to you so far, Spitzer and Hubble, were not sensitive enough. Hubble can't see in this region, but James Webb will do, for instance. And Clara, who is currently at Harvard, actually developed some work on phosphine as a biosignature, particularly in planets which have life but no oxygen. It's thought that phosphine could be really important. Little did she know, though she was involved in this work, there was a claimed detection of phosphine in the clouds of Venus, which the authors of that paper have associated with life. I remain very agnostic on that, and actually their detection used a single transition right down here at very long wavelengths. So the detection itself has been challenged, but it's certainly an interesting topic. The real molecule, when we ran a ExoMol conference right at the beginning of our project in 2012, and we asked our speakers to say what molecule they needed a line list for, and our last speaker came up and said, I only needed a line list for 3 molecules, methane, methane, and methane. So we got the message, and we went out and made a really concerted effort to make a good methane line list. Now, this is a 9-dimensional potential energy surface, so we had to do 130,000 electronic structure calculations. Luckily, on compute farms, these are parallel jobs, so you can maybe do 1,000 of them at the same time if you have a big enough computer to do this. And we did similarly the 9D dipole surface, also needing 130,000 geometries. In this case, we did them at the same time. We adapted a version of the Trove program to work for methane, again putting in the full symmetry. In this case, that had quite severe consequences for the structure of the program. And we produced a line list which we called 10 to the 10 because it had approximately 10 billion transitions, actually 9.8 billion transitions. And here, if you compare coverage with Hytran, you can see that we got lots of transitions that are not there, and in particular at higher temperatures, these are really important. So this is the absorption spectrum of methane as a function of temperature, and you can see that you're getting changes of tens of orders of magnitude. About 10 orders of magnitude here when you go from room temperature 300 Kelvin to say 2000 Kelvin, and the whole spectrum flattens out. And if you do some actual modeling with this, you can see a huge difference. So this is a spectrum of a brown dwarf. Brown dwarfs are failed stars that were detected only about 30 years ago. And this is a T4.5 brown dwarf, which are known to be very rich in methane. They're called methane dwarfs, and it was observed with the IRTF telescope in Hawaii. And this is the spectrum. And when it was published, this observation was published. The best spectral model that was available at that time used a so-called STDS methane line list. And basically, this methane line list was a compilation of all the known lab spectra of methane. And you can see this is not a very good fit. When you do the same thing with our ExoMol methane line list, you can see the fit is pretty much damn perfect. And this is really pleasing. Now, what wasn't so pleasing to Jeremy Bailey, who did the modeling here, was that he tried throwing out most of our 10 billion lines and it didn't work. So he gradually put them back in and put them back in. And it was only when he retained 3.2 billion lines did he get a good fit like this. And he does not want to run radiative transport models with 3.2 billion lines, but the reality is, to get the opacity right, you have to consider a very large number of weak lines. And our line list is not only good at doing the total global opacity, but you can see at moderate resolution like this is a resolving power of about 3000. We also got rather nice agreement with the observations. So the ExoMol project has produced a large number of line lists. Never, when I started, thought we'd be publishing line list number 44. In fact, I discussed line list number 45 with one of my postdocs this morning. So we're still producing these line lists. Our to-do list probably hasn't got shorter over this time, because as fast as we do line lists, people come to us and say, yes, but we need a line list and so forth. And in particular, the discovery of these Cult 4b and other very hot gaseous rocky planets has opened up a whole new area of trying to look at strange molecules like zinc oxide and zinc sulfide, which we hadn't imagined when we started the project in the first place. And also we've been extended increasingly line lists into the ultraviolet because people want to know the data at these longer wavelengths. So that's where we are. We're still working hard at this, and we're on a cycle of doing 4-year data releases. So we did a major data release in 2016, and then in 2020, that's republishing the whole database. But we publish the individual line lists as a series of papers in monthly notices of the Royal Astronomical Society as we go on. And the ExoMol database, which is lovingly maintained at this website, contains the line list, cross functions, partition functions, broadening parameters. We need to do more work on that. K-tables, if you don't know what they are, remain happy and don't find out. Lifetimes for individual species, cooling functions, Landé G factors, important if the molecules are in atmospheric fields. Various physics projects, particularly the Rich Mol project from Andrei Yakhmanev, who is now in Germany, but was a fellow in our group for a while, uses dipoles to look at molecular orientation effects and molecular control. We have an application program interface, because I believe if you have this amount of database data, you should be talking computer to computer, not to the database. We have opacity tables recently compared. We've just made a lifetimes database for plasma modeling, and we're in the process of constructing a high resolution database for reasons which will become obvious as I talk on a bit further. But just as an aside, a couple of years ago, we made the first detection of water in a habitable zone exoplanet, made with my observational colleagues, Anglos, Ingo, and Giovanna. And this was published in Nature Astronomy, and interestingly became UCL's most reported scientific result, beating the detection of the oldest discovered dinosaur by a factor of 2. So there's real interest in these sort of discoveries in exoplanets, and we spent a very interesting 2 or 3 days dealing with the world's media. So as known in 2019, there were just over 4,000 exoplanets, and for many of them we know how big they were, how hot they were, and how much they weighed. So we knew that much. You could get that, as I've already explained, from looking at the transits and the radial velocity measurements, and then you could begin to get galactic statistics, and actually a lot of these now are known to be super Earth exoplanets, planets that are a bit bigger than Earth, and they have a rather strange distribution of these. There's a minima in them at about 1.8 Earth radii. I'm not going to discuss that here. So the next questions, of course, are what are these planets made of? What is the weather like? Why are they so diverse? How do they form? And of course, as raised in the introduction, we'd all love to know if they're habitable and even inhabited. So that's very much the goal. So we had these observations. I'd collaborated before with this group on doing a systematic study of hot Jupiter planets, for instance, looked at 40 type Jupiter atmospheres, found that we could detect water in a lot of them, titanium oxide in some of them. And in this case, they did repeat observation using Hubble telescope, or using data from the Hubble telescope, to model the water signature in this planet K218b, and they see here a definite peak here, which is a clear sign of water. However, as I'll explain in a minute, it didn't tell you much more about the planet except the fact there's water there. So where is this planet? It was discovered only in 2015, actually, by the Kepler mission. K2 is the second part of the Kepler mission. It's in constellation Leo. It's about just over 100 light years away. So it's a small, rather insignificant star that happens to have a planet orbiting it rather close So the planet itself is in the habitable zone. Now this planet is not an Earth 2.0 because it's actually 8 times the mass of the Earth. Sorry, I clicked too far there. So it's 8 Earth masses. It's much bigger than the Earth. It's orbiting its star much nearer than the Earth is orbiting the Sun, because K2-18 is a much smaller planet. It's a cooler planet, which actually means you get a bad space weather forecast because it's going to be bathed in UV radiation. But from an observational point of view, it's great because it has a period of just about a month, so you can observe it 10 to 12 times a year and get a lot of data quite quickly. And so we're looking at a habitable zone. What does it mean? It means the estimated temperature is suitable to have liquid water. So we know that we've got this in this particular planet because of where it's orbiting. We now know that from the observations, we know that it has an atmosphere. We know it has water. We don't know it has water organic chemistry. We don't know it's a stable environment. We don't know that it's inhabited. The observations were made with Hubble, as I mentioned. The original data looks absolutely revolting. It looks like this. Hubble was launched before anyone discovered an exoplanet. It was not designed for making these observations. You have to so-called detrend the observations to get the data out. Anglos spent a lot of time doing this with 8 different observational visits. When he's done that, you can see nice transit curves here. And it was these transit curves he was able to extract the data that allowed you to look at these observations to get the size of the planet as a function of wavelength. And this is what we then modeled. And we had 3 models: a water hydrogen atmosphere, a water hydrogen nitrogen atmosphere, and a water with high altitude cloud atmosphere. And they all are consistent with the data. We can't tell the difference between them just using this single set of observations. So what we desperately need is some new telescopes to do some observations. Luckily, this is happening. So with ability to look in the mid-infrared, we should be able to see other molecules, so things like water, methane, phosphine, ammonia, all the molecules I've been talking about, a bunch of diatomics. But we really need to get in space to do this, because it's very difficult to do from Earth, because you're trying to look through the Earth's atmosphere to make these infrared observations. Unfortunately, we have a raft of telescopes going to do this. Maybe in 2 months' time, it's scheduled to launch the James Webb Much Delayed Telescope. It's going to be used 25% for exoplanetary time. It's going to be great. It's also going to be very frustrating, because the amount of observations people want to do with James Webb and the amount of observations that are going to be doable with James Webb are completely out of kilter. But we will get the beginnings of really good infrared telescope. Resolution maybe about 3,000. So we should be able to detect a whole bunch of molecules in there. And looking at this, looking a little bit further ahead, we've got the Ariel space mission, led by my colleague Giovanna Tonetti. That's scheduled for launch by the end of the decade. It's an ESA mission. It's going to be a dedicated exoplanet mission. You'll have serious surveys of maybe upwards of 1,000 exoplanets, so that will be great. Me and Giovanna are also working on trying to do a cheaper, quicker mission called Twinkle. We've actually had quite a lot of discussions with the Indian Space Agency and the Indian Institute for Astrophysics in Bangalore about getting involved in this mission. So if people are interested in actually this mission, please contact me afterwards. It's the idea here of actually doing a rapid space mission where we charge for the data, so people take a subscription to the mission and get involved in it. And we have a company, Blue Sky Space, for managing the mission. So that was the first phase of ExoMol. This was the group I assembled. They all got molecules to make line lists for. They even had names as well, and that were a great group, and they got dispersed. And then I went on to ExoMol 2, which started a year ago, so-called ExoMol HD, which was precision spectroscopy for studies of exoplanets. And I'm going to talk just about 2 of the topics here: line lists with spectroscopic accuracy and photodissociation, the pressure broadening. We've recruited a postdoc. He arrived at UCL this week, so we're just starting that, but we haven't done any work on it yet. Why do we need high precision spectroscopy? Because about 7 or 8 years ago, a gentleman called Ignaz Snellen from the Netherlands came up with a really neat method of detecting molecules in exoplanets. And what they do here is they look at the absorption spectrum as the planet orbits all the way around its star. It doesn't have to be transiting, but what you get is a Doppler shift in any molecular features as the planet orbits. So you can do this even if there are telluric lines, Earth atmosphere absorptions, giving this black line here, because of course they don't shift as the planet orbits. Now, normally you don't see any actual signal here. Normally when you do this, you get white noise. And what you have to do is make a high resolution phase mask for the molecules, so you get something looking much more like this, which looks completely horrible when you start off with. And as you put in the molecular lines, you begin to see, using a phase mask, you begin to see the idea of where the molecular absorptions are. But this only works at very high resolution. Resolutions of 100,000 or better are really the best way of doing it. So if we're going to use our line lists need to be really accurate to do this. So we were faced with the idea of actually improving our line lists, our line positions in the line lists for Hubble, for James Webb Telescope, and for Ariel, which are resolution 3000 missions. Our current line lists are really good enough for this high resolution stuff. We're not at accuracy at 100,000. We're maybe 10,000 to 20,000 in most cases. So we got that far by refining the potential energy surfaces. I already told you that. But what we've discovered is we can substitute experimental line positions into our final results. So we've been doing this, and to do that we developed, I developed with some Hungarian collaborations a procedure called MARVEL, and that has measured active rotation vibration energy levels where we invert the experimental data to give us very accurate energy levels, which you can then put back in our line list, and that gives us very good predictions of experimental transition frequencies. And we have a variant of this we should use for isotopologues. I'm not going to talk about that today. So we've done a bunch of these measured active rotation vibration energy level projects, MARVEL projects. It's rather labor intensive. A colleague of mine from the University of Dijon, a collaborator of mine, described this as spectroscopic archaeology. You spend a lot of time in the literature digging out all the measurements. I think the oldest we've used goes back to 1930. Quite a lot of very interesting solar data actually coming from India, which have been used to input for molecules like silicon oxide. Because this is labor intensive, we had the idea of recruiting a number of school children to help us with. So a number of these projects has been run as a part of the Orbits program, original research by young twinkle scientists. And that was dreamt of by Clara Souza Silva, but is still going on. It's under other management. And in fact, won a national award this year for the best outreach project with school children. And we published a number of papers. The school children are co-authors on all these papers highlighted in yellow, and there are several more coming up on the MARVEL project front. So what does MARVEL do? Well, this is just an example using formaldehyde, which we published earlier this year, where we capture data from 43 sources listed down the right-hand side. We validate the data. So what you got here is 3 columns. The first is the number of data. So in this particular example, 3,149 transitions, of which 3,128 turned out to be correct according to us, got validated. So we validate all the transitions. That gives us a database here of about just under 17,000 unique transitions. That gave us a bit over 5,000 energy levels. When we put that back into our ExoMol line list, we actually found that we could get 360,000 transitions predicted with experimental accuracy. And you may think many of these are very weak, but actually half of those are above the Hydride cutoff for inclusion at 296 Kelvin. We just missed the 2020 release of Hydride, but they're very interested in including our improved formaldehyde data in the next issue of Hydride. So that's just a terrestrial result, but obviously that gives us also a lot of data that can be used for doing high accuracy observations. So that will be done, and that's ongoing. And then as a final project to talk about, we started a new project looking at photodissociation. So photodissociation is when you wind up the wavelength of the, you wind up the frequency of the light you're shining on your molecule, and that results in the molecule photodissociating like this. We're not so interested in the multi-photon dissociation, but we are interested in either the direct or the indirect photodissociation, as it's important for exoplanets, because for many of these exoplanets that I've just discussed before, they're orbiting very near their host stars. M dwarfs, for instance, which are of particular interest for looking for habitable planets, have a well-known excess emission in the ultraviolet. These ultraviolet radiation causes photodissociation of the molecules in the atmosphere. If you're going to get the chemistry of these planets right, you need photodissociation cross-sections. And the interesting thing is a lot of work had been done on photodissociation in things like the Leiden database for the interstellar medium, but these data have been firmly assuming that the molecules are effectively at 0 Kelvin. For most practical purposes, 0 Kelvin and 300 Kelvin don't make much difference for most molecules, but 1,000 Kelvin, I'll show you this in a minute, makes a big difference. My back of the envelope calculation was that if you had a hot Jupiter orbiting the sun, you could get molecular photodissociation rates which were factors of 50 higher than they were in the Leiden database, just because of the temperature effect on the molecule. And I'll show you that this has turned out to be true in our calculations. So we had to go away and adapt some programs for doing photodissociation. And for those of you who are doing electromolecule scattering, you'll know that you have to do this whole continuum processes going into the outer region. I decided that was going to be a lot of work, and we tried plan A, which actually just ignored the outer region, and we simply flooded an inner region program with these continuum wave functions. And we have our ground state wave functions here, and we looked at the transitions between them, transition dipoles between them, and calculated the transition intensities. So we adapted our program Duo for doing this, and then we post-process to get line profiles using our post-processing program ExoCross. And you start off with something which is a discrete set of lines like this, and you plonk a Gaussian profile down it, and this seems to actually give results that really match the experiment. So here's a comparison, I think, for HCl. I haven't put on the, oh yes, here it is, HCl. This is HCl here. And when we do the Gaussian smoothing, we get really very, very good agreement with experiments. With other codes that do photo, does the full calculation going to the outer region, that it doesn't do the temperature effects. Photo will only work at 0 Kelvin. So we started then looking at the effective temperature, and for that you need to consider what the black body curves are, and of course that depends on the star type. So you can have 4,000 Kelvin stars such as T Tauri stars, you can have A-type stars at 10,000 Kelvin, or you can have the very hot B-type stars. The interstellar medium flux they use tends to be from these very luminous blue stars, but that's probably not so important for exoplanets. So we went away and we've done a number of molecules seriously. The first one we're looking at is HCl and HF, and here you have now a whole lot of curves here that we need to consider, and the dipoles, and we're fortunate enough that these have been published. So we here looked at the different isotope log effects, and indeed deuterating the molecule does matter. Going from chlorine 35 to chlorine 37 is really a rather minor effect. But what's interesting is when we look at the photodissociation rate as a function of what the flux is. So if you use the interstellar medium flux, which is these very hot fluxes from very hot stars, it actually doesn't matter very much what the temperature of the underlying molecule is. But if you look at a 4,000 degree star, or indeed a solar flux, what you can see is you get a huge temperature dependence. We're increasing by a factor of 50, as I predicted, between just below 1,000 Kelvin going up to a few thousand Kelvin in the photodissociation rate. So we're just writing that up to be the first one of a new series of ExoMol studies, ExoMol photodissociation cross-sections, with my postdoc Marco Pizzella having done the work on doing that. So I had the strange experience of trying to start this brand new project under lockdown. So this is virtual ExoMol tea from a year ago, where we all met on Zoom once a week for a communal activity, had to provide your own tea, and here we all are. We've just, UCL opened up fully about 2 months ago. So we're now getting back to actually being able to meet in person, though socially distanced. So this is the current group who were at ExoMol tea in person a week ago, but instead of taking a group photograph, which put us all together, we took individual blue screen photographs. So here we are, a montage of us all. So I must thank them. I must thank the previous ExoMol workers working together, and a few hardy people, Sergey and Oleg, who've come through both of the projects. And I must thank you very much for listening to me. Thank you. If I'm allowed to end on a brief advert, sorry, I didn't mean to press that button.
Thank you,
If I'm
Professor
allowed to
Jonathan.
end on if I'm allowed to end on a brief advert, if you're intrigued by astronomical spectroscopy and you don't know much about it, I have an introductory textbook you're welcome to read.
Yes.
Okay, thank you.
Oh, thank you. Thank you, Professor Jonathan. Yeah, I forgot to mention about your 2 books. There's one more book, right?
No, there's 3 editions of this book.
3 editions, okay.
Yeah, but it's all the same book.
Okay. Thank you. And we'll move to the questions now. We are open to questions from the panel today. And then I'll read out the questions from the YouTube. So members can unmute your mic and you can directly ask or speak up.
If I may.
Yep, please do.
Yes. Thank you, Professor Tennyson, for this intriguing, wonderful talk. I was particularly amused with what you said that you involved the students to do the science. Could you please elaborate on that? Like, what was the task given to them and what did they do?
Okay, so what a Marvel project involves is surveying all the literature to find papers with spectroscopic data in them. So what you do is we normally brought the students into UCL for an initial visit, a briefing, have a look around because they're interested to go to university. We told them about the project. Then they meet in their school once a week. We use PhD students as tutors who go to the schools once a week. They start off by all doing a search, normally using Google Scholar to find spectroscopic papers. These are all assembled together. Normally, to be honest, I or the PhD or both of us have to do an extra search just to make sure we've got everything. The students then get divided up into either groups or individuals, and they get 1 or 2 papers each. They extract the data from this paper, they interpret it, they put it into a standard Excel files sheet format that we can then use as the input to Marvel. We then start feeding the data into Marvel and looking at the data. And normally, which is why the students aren't first author. Normally the PhD student is the first author. The PhD student has to finish off the Marvel process at the end of it. But that's a life cycle. But having, say, 6 to 10 students in parallel processing data really helps the project move forward.
Yeah, okay. Thank you. It's very interesting how you got the students involved, and I think it's a very learning experience, for them, and this particular information.
And I'm sure you have the same issue in India. We particularly have schools which don't have a good record of tending students to do science at universities. And we've focused on those schools. It's been a deliberate aim to actually try and engage, not with the schools which have children from very rich backgrounds who have lots of opportunities, but actually go to schools which have lower educational opportunities. Of course, in London, you have the whole range, so it's very easy to pick your schools. And it's really been transformative for some of the children. It's very interesting. They got very involved with it, realize that they can do high-level science. You don't have to come from a particular background. If you've got the skills and the interest, you can do it.
Yeah, wonderful. Thank you very much, and congratulations on that. Yes, Bala. Well, there are some questions, Bala, on the YouTube that probably you can pick through.
Sorry, my mic was mute. I'll read the questions from YouTube. Before that, we will have any questions from the panel members.
I have one question, sir.
Okay.
Yeah. Professor Jonathan, you search for biosignatures such as phosphine in some of the planets, but you could not detect them in SPICR as well as in Hubble. It's primarily due to the sensitivity issue or any sort of other issues were there.
Right. So let's be clear. I'm not really. I collaborate with observational astronomers, and 20 odd years ago, I did go observing a few times, so I'm not really an observational astronomer. So I personally have not been tried to detect trying to observe phosphine, but people have. And the real problem with Hubble is that Hubble doesn't go into the mid and far infrared. So Hubble, the shortest wavelength the longest wavelength you can look at in Hubble is about 1.3 microns. And that's turned out to be quite suitable for looking at water. And you can get the odd hints of other molecules, titanium oxide, vanadium oxide, and maybe even methane. But phosphine simply doesn't have a good signature there. So you need to be at that 4.5 micron region to see phosphine. And I think, I hope that the James Webb Telescope will make a phosphine observation fairly early. I think it's reasonably low hanging fruit in terms of being observable because it has this very nice sharp feature in there. But we will see. Not long to wait. Well, 2 months till launch, maybe this time next year, we'll be beginning to get good James Webb data. So I think it's one of many, many things that I think James will do for us.
Okay, so I have another questions. May I proceed, Bala?
Yep. Yep. Ask away.
Yeah. So I saw a beautiful, IRTF spectra on brown dwarfs, and it is matching very well with your ExoMol data spectrum, isn't it?
Yep.
So yeah, so my question is whether one can apply this ExoMol data set to other low mass stars, even to high mass stars?
Absolutely. So to be honest, I started off this project, I was looking at cool stars. So when we made the BT2 line list, it was aimed at M-dwarf stars. And indeed, titanium oxide is important in M-dwarf stars. So yes, you can certainly, basically, as long as a star is cool enough to have molecules in, you can apply the data sets to it. And, our aim when we do it, because doing a calculation takes a lot of time to get it right, our aim is to try and make it as widely usable as possible. So people come to us and say, this is what we need. So for instance, we're redoing the magnesium hydride to go into the ultraviolet at the moment. One of the reasons for doing that is it turns out that people use magnesium hydride for detecting magnesium isotope ratios, which is important for modeling stellar nucleosynthesis. So we've actually had a project to redo the ultraviolet spectrum, and we're making sure we do it for both magnesium 26 and magnesium 25 so that people can do those observations. And that actually came about because people approached us after we did the original line list and said, yes, but we want the UV spectrum and we need these different isotopes. So we're quite amenable to doing this. So this is funded as an ExoMol project. Basically, I want people who are interested in using the data.
Thank you. Thank you.
Thank you. Before we move to the next questions, we just got some information in the YouTube. We'll congratulate Professor Jonathan Tennyson for being the first editor-in-chief of the Royal Astronomical Society's new journal on techniques and instruments. First time they're releasing a journal in 100 years. Congratulations.
Yes, indeed. I'm editor-in-chief of this new journal, which website is going open on the 16th of November, so 3 weeks. And I hope that some of you will submit papers there because we're looking for good papers. So please feel free to. And it's particularly aimed at sort of methodological papers. So for instance, publishing our computer programs, but also machine learning, data analysis, instrumentation papers that are difficult to place in the journal. And indeed, it's interesting, the Royal Astronomical Society is nearly 240 years old. And this is only the 3rd journal they've launched. So it's nearly 100 years since they last launched a journal.
And thanks to Professor Deepankar Banerjee for pointing this out, which we missed earlier. Thank you. Yeah. Okay, we'll move back to the questions. I have a few questions. If no one in the panel has questions, I'll ask them, and then we move to the YouTube questions. Okay, I'll start with the first one from me. In the molecular thermometer slide, you have shown the scale from 0 to 8,000 Kelvin. So is there a reason why we stop at 8,000 Kelvin?
Yeah, I think there aren't many. If you're in LTE, I don't think there are many molecules above 3,000 Kelvin, maybe carbon monoxide, but they tend to just boil apart. I mean, it's very interesting looking at the sun and sunspots. So the sun itself has a few diatomics in sunspots, silicon oxide, water, very strong species. So that's the difference between maybe 3,500 Kelvin and 6,000 Kelvin. But by 8,000 Kelvin, there aren't many molecules left.
Okay, thank you. And then the next one is about because we work on the molecular ices. Why it is so hard to model the molecular ices? There's a lot of modeling is going on.
Well, it's, you could see that I'm looking at, say, methane with 10 electrons and 12 degrees of freedom, and this was already a major calculation. The molecular ice, you've got the whole property of what the ice looks like, which is not even that well. People make it in the lab, but the reality of astronomical ices are layers of different species, almost certainly on top of each other. So and then you've got the process of the molecule absorbed on the surface. It's a very complicated situation. So the level, I am trying to do calculations where it almost makes it unnecessary to do experiments because they're that accurate. I think for something like a molecular ice, you're a long way from being able to do that because they're such complicated systems. So it's much more trying to interpret and understand, but they're very complicated to look at. So I have my deepest admiration for people who can do good models of molecular ices, because they're difficult problems.
Professor Tennyson, can you hear us? We lost your signal.
Yep. No, okay, I can hear you.
Okay. Yes. The third question is the general one. Can you please comment on the phosphine in exoplanets?
Phosphine in exoplanets or phosphine in Venus?
Both.
So exoplanets, we're still waiting. I mean, I think phosphine will be discovered, but we're still waiting for the discovery. The Venus is a very interesting one, because there's been a lot of attempts to prove that this observation was wrong. And I have to say the original observers have put up very strong arguments why they believe what they've done is correct. So I don't like one-line observations. I think they're dangerous. Molecules have very rich spectra. And that's one of there are many problems with working on molecules, but one of the advantages is you should be able to see a whole set of lines. So you should be able to see a lot of transitions like this. And then you have very firm detections. So one-line detection is worrying. So I think it really needs further detections in other lines. And the interpretation, I think, is difficult. It doesn't necessarily mean it's wrong, but no one else has put out a different interpretation. If it's right, it's really transformative. But I think it still needs a lot of proving. And that's to say, I think this is a paradigm for what it'll be like when molecules are first claims of detection of life in exoplanets. It'll be slightly tenuous at first, and a lot of people will come up with other explanations. It'll take some time before you really get to say, yes, that exoplanet quite clearly and beyond all reasonable doubt has life on it. So we'll go through the similar sorts of arguments. I'm looking forward to it. I hope I live to see it. That's all I can say.
Okay, thank you. Right. So I will now read the questions that we have got from the YouTube chat box. The first question is by Dr. Vijay Sahu. What type of Minibody method is employed that requires such a huge amount of memory to store the wave functions? Are these wave functions temperature dependent?
So the wave functions aren't temperature dependent because we do time independent calculations where we get all the states of the molecule. So the temperature dependent we put in afterwards by the way we model using Boltzmann statistics. So by the way we model a spectrum, we put in the temperature dependence. The wave functions are effectively representing the nuclear motion at a grid. And the different programs we use subtly different grid methods, but they all use grid methods. So what you're getting is an amplitude of a wave function at a grid. You get lots of these levels. I mean, so I said for water, in fact, we've redone water. We now have our latest water paper has a million states in it. So we're saving the wave functions for 1 million states, and each of those states may be half a gigabyte to store the wave function, or a gigabyte to store the wave function, and that's all the all the grid points you put the wave function at. Now you can cut them down, but if you do that, you lose accuracy. And we try very hard to be as accurate as possible. So, I mean, I commented that we were putting data into Hydride these days. Our major contribution to Hydride is actually that they're replacing our calculated transition intensities. They're using our calculated transition intensities instead of measured experimental ones, because we can very often calculate them to better than 1%. And that can only be done with very specialist experiments, which maybe do a few lines, whereas we can do all the lines. And to do that, we need very accurate wave functions, which is why they get very big. Okay, so we use grid structures. You can think of basis sets spread over a large range of coordinates. And these basis sets, electronic basis sets, are extremely efficient. Our basis sets are rather less efficient, but the motions are rather complicated. Okay.
Yeah, and I'll move to the next question from Dr. Vijay Sahu again. Would it be better to use the relativistic version of Minibody method to account for the spin orbit interactions more accurately?
That's a very good question. possibly. We certainly are playing around with different relativistic methods. And if anyone can, look, I'll give you a slightly easier problem. I was talking with my postdoc this morning about doing nickel hydride, and he was struggling using standard CAS-SCF, MRCI methods to do nickel hydride. The problem we need is we need many electronic states. So we're not just looking at the ground state. And the quantum chemistry methods people are using are very often not well tuned for this. I think, to my view, the quantum chemists have slightly taken their eye off the ball on this problem because they pursued other problems, normally larger molecules. But we really struggle to get good methods. So if someone can find us a good method which does the spin orbit interactions and does the excited electronic states well, we'd be very interested. There's certainly scope for using different methods than the ones we use.
There is a follow-up question. In your analysis of observational data, how isotope shifts play the role?
Right, so the isotope shifts change because the molecular wave functions change. So it comes in from the second stage. So basically, I mean, at the simplest level, you simply, if I said going from magnesium 26 to magnesium 25, you simply change a number in our code and rerun the calculations and they shift. And the rotational spectrum is directly proportional to change in reduced mass. The vibrational spectrum is proportional to the square root of the reduced mass. But these shifts, for instance, in the interstellar medium are very well known. People look at carbon 13, oxygen 17, and so forth. The first observation of an isotopically substituted molecule in an exoplanet was made last month. It was reported in Nature, and it was carbon 13. We, for instance, are in the process of preparing a very good HDO line list that people can look at for deuterated water instead of normal water.
Okay. I'll move to the next question by Raghav. I hope we have time for 3 more questions.
I've got plenty of time, so
okay,
just
thanks.
fire away.
Okay, this is from Raghav. For phosphine, was the detection was ortho or para considered? What detection do you consider ortho?
Right, that is a very good question, and I could only answer it by going back and reading the paper. I mean, statistics would suggest it's para because that's more likely, but actually, I don't know. I don't remember that. I did look at what the line was when they first made it, but that was a year ago.
Okay, and then as a follow-up question by Raghav, the potential energy surface, was it averaged over the vibration states?
No, so we use the potential energy surface to compute our vibrational states. So the potential energy surface is an input to the nuclear motion program. And then some properties you can get by averaging properties over the vibrational state, but we don't have vibrationally averaged potential. We use that as so we do a full quantum mechanical solution of the nuclear motion problem. This is the thing that leads to these very complicated wave functions to give us our low vibrational energy levels and wave functions and intensities. So yeah, we don't average the potentials.
Okay. Then we have a question by Dr. Namit Mahajan. How are finite temperature effects incorporated in the ab initio calculations?
No, so we do everything. I think I answered a variation of this question earlier. We do everything temperature independent, and then the temperature effects come in the modeling at the end. Now, the only thing the temperature is included in is that depending on when we do a calculation, how hard you work can depend on how big a temperature you get at. So basically, you go up in temperature as you make a more and more complete line list. So if you have a line list that's good for 1000 Kelvin, it's absolutely fine for 300 Kelvin and 10 Kelvin. But if you have a line list that's good for 10 Kelvin, it'll very, very rapidly become not good for higher temperatures. So the temperature comes in and how we choose how many energy levels we look at, how high we go in things, but the calculations are done temperature independent, and then this program Exocross, which I mentioned briefly, uses Boltzmann statistics, or indeed we're looking also at non-thermodynamic equilibrium models of spectra. So we put in the temperature or otherwise at the point where we model the spectrum at the end.
Okay, thank you. And there's one more question by Dr. Vijaya. Are you using analytical basis functions like Gaussian functions or numerical basis functions? basis
Right.
function?
That's a good question. The short answer is basically we use grids based on analytical functions. The longer answer is quite a lot more complicated. So Level, which I mentioned, which is not our program, actually does a direct numerical integration. Duo, which is our diatomic program, uses a sync DVR basis, so uses sync functions. My code DVR3D, which does triatomic molecules very accurately, uses Gaussian basis sets, but we then turn that into a discrete variable representation to give a good grid representation. And Trove generates its own representation, but similarly uses DVR representations of Gaussian type functions. So it is basically analytic functions, which we then turn into DVRs. Is the most common method. And we try and adapt these for the situation we're looking at in the molecule.
Okay. And we have two questions, which are in fact the same. So I'll read it out. This is from Dr. Vijaya and Dr. Sashikaran Ganesh. It's about the upcoming journal from RAS.
Yep.
The question is it free of charge? Do we need to pay for the charges?
It's open access, so I'm afraid you have to pay. However, we are aware that paying is not the same all the way around the world. So there are special measures in place for countries which would find this difficult. And also in the beginning bit, I have the ability to accept articles for free. So if certainly in the next year or two you're interested in publishing a paper, you may, and paying is an issue, you may want to just email me, because I may be able to say, yes, we'd love that paper, and I can waive the page charges, because that's one of the perks of being editor-in-chief, that I've been given a budget to spend on good papers to get the journal running. But we're also aware, in fact, I was carefully to take one of the board members from Africa, because I was very concerned that, it's one thing to make the journal open for all readers, but I don't want to make it closed to half the scientific community. So I was very concerned that paying would be accessible for all. And this is a policy. There is a policy, and we're also working on the policy. So if you have any concerns about paying, just contact me privately, and I can advise.
Thank you very much. Thanks a lot. I'll now pass it on to our colleague, Dr. Navinder, for the vote of thanks and concluding session.
Hello, I'm audible? Hello? Yeah.
Yes, I can hear you.
It's my pleasant duty to say vote of thanks. On behalf of our Director PRL, Dean PRL, and my colleagues in the Amrut Vyakhyaan Committee, I thank you, Professor Jonathan, for this wonderful presentation on exoplanets. I thank you for your time, for your effort devoted to this Vyakhyaan. I would also like to thank our Director, Professor Anil Bhardwaj, our Dean, Professor Pallam Raju, and Chair Amrut Vyakhyaan Committee, Professor Nandita Shrivastava, for their support. And I especially thank Professor Nandita Shrivastava for her enthusiasm and her constant efforts to keep this show running, this series running. So with this, I'd like to thank you all for your participation, and all the participants who asked questions. So this is an excellent session. A lot of discussion it generated. And one more time, I thank you, Professor Jonathan, for your time and your effort to deliver this nice Amrut Vyakhyaan. Thank you very much.
Okay, well, thank you very much for hosting me, and can I congratulate you all on your 75th anniversary?
Thank you.
Thanks a lot.
Thank you, Mr. Jonathan.
Okay, goodbye.